I hope I find everybody well. Surviving the last 2 weeks of classes is no easy feat. So my thoughts are with you, and good luck wrapping everything up. Just maybe just as a reminder here. So really the only thing that you have to worry about for this course is finishing off that lab, right? The pendulum experiment, part 1 and part 2. We spent some time talking about that. The most important thing to do is to clearly explain your logic behind the choice of your tool and your method. If you read any scientific paper, that section of it called materials and methods is probably the most important section of a paper when it comes to getting something peer reviewed. You know, if you're saying that this sample size is good enough to be 95% confident, they're going to want to know why do you think that, right? What assumptions have you made? What decisions are you making? You think also just in terms of math in general, from a philosophical point of view, math provides models and graphical predictions and algebra algorithms that allow you to simulate this universe that we live in. When you are, trying to back up your claims, right? That's what it really comes down to in a statistics course. When we're trying to back up statements or numbers, you just want to be as detailed as possible as, about what was your thought process. Just to refresh your memory, this whole slide presentation is talking about a data set that has a fairly small sample size. Which is similar to your lab, right? I think the sample size in your lab is also 5 for part 2. And as you guys know at this point, that's small, right? And so it's really hard to prove anything with a small sample size. And the R value that they get, or that we get, when you try and correlate shoe print size and height, as you would expect, is relatively small as well. Now, the reason this is small is because, well, partially because the sample size is small. If you increase the sample size and you had the same type of correlation, this would increase. Again, it's kind of like sample sizes with anything else we've done, right? If you have a larger sample size, gives you a better estimate on the actual error, for example. So, I mean, this is going to be a weak correlation at best. Because in general, any value below, I don't know, I'd say 8 is going to be considered weak. However, it could still be significant. Kind of like in relationships that you may have with an ex-girlfriend or boyfriend, right? It was weak. It was a weak relationship, but it was significant. So that's the real question. You can have a weak, significant relationship. But we have to test it. It doesn't look good. That's basically what I'm trying to say right now, is it doesn't look good. But in order to figure out if it's significant or not, you do a hypothesis test. That's basically the hypothesis testing in general allows you to figure out significant results versus non-significant results, right? Again, you can have, if you just think back to chapter 8, right? Let's say that your null hypothesis, go back to chapter 8, or even just let's think of that that question in the quiz where it was, all these drug concentrations of RNA, right? You can say, all right, we have something like, 15 milligrams of RNA per vial of vaccine. And let's say you do a sample right? You do your sampling and you find that it's actually something like 18. Well, it looks like it's higher, but there's all these other things that are factors, right? You say, well, maybe your sample size was small. Maybe the standard deviation is large. And so you want to know if this is statistically significantly far enough away from 15. That's the whole process, right? Your alternative hypothesis when you're doing these things is, in this case, you want to say, well, does the 18 imply that it's actually greater than 15? Right? We can't, if you go back to the nature of hypothesis testing, we can't prove that it is 15, or sorry, we're not trying to show that it is 18. We're trying to show that's bigger than 15, because again, this is just from the sample, right? This is just a statistic from the sample. It's not a parameter of the population. I'm sure Johnson and Johnson is worried about this right now with their blood clots, right? Is that a big enough sample to say that it does cause blood clots? More than normal. I'm sure they got people working around the clock right now at AstraZeneca and Johnson trying to figure this stuff out, right? Just because you have 20 blood clots out of 100,000 people, is that statistically significantly more than the normal average number of blood clots? That'd be a good final exam question, right? How many blood clots do occur in 100,000 people? And does the sample that we're getting here, is that statistically significantly higher? Or is it just, I don't know, something else? Could be related to something else. So there you go. But in this case, so this would have been like a chapter 8 problem, right? But as we move onwards, so in chapter 10 and next week in chapter 11, we also do hypothesis testing. But it's going to be of a different sort because it's always the same in this case. So when dealing with chapter 10 hypothesis testing, the null hypothesis is always, 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 always that there is no correlation. And again, this would be probably something that Johnson and Johnson would be doing right now. There is no correlation between vaccine doses and blood clotting. And because why would there be? Right? Again, the null hypothesis is kind of this, you're playing the devil's advocate. I kind of was thinking about that last night. You know, I was mentioning before, you know, status quo is a good way of looking at the null hypothesis, or past behavior, you know, past information. Another good way of thinking of the null hypothesis is like the skeptic viewpoint. You know, it's funny, we say now that skeptics are people that believe in conspiracies, but true skeptics are skeptical of conspiracies, right? I mean, if you told me there's a correlation between blood clots and vaccines, I'd say, I don't believe it. Why? Why would there be? It just sounds like you want to make some money and sue a vaccine company. But the skeptic point of view is no, essentially. Like you know, if you really dig down, a skeptic says no to something, not yes to something. And your alternative hypothesis in all cases with chapter 10 is always, it is not zero. In other words, we're going to do a two-tailed test. I apologize for writing over everything here. That's not very nice. But I would clean this up if I was trying to submit this somewhere, but that's good enough for now, right? So essentially, this is your hypothesis. Either there is or there is not a relationship. The status quo or the null hypothesis is there is not, and I want to prove that it is not zero in a significant way. So the quick and dirty way to do this, and again, we'll call this the easy way. So why not? The easy way is if you're testing for a correlation with a significance of either 0.05 or alpha 0.01. If you have either of these conditions, so if it says is it significant or not, and the alpha level is not specified, so you can just assume 0.5 or 0.01, however you like, then you want to use table 5 in your formula booklet to find the critical score of R. So our sample size in the right here, this is your beautiful cheat sheet right here, the easy way. What are your critical values of your correlation coefficient? So we basically just need our sample size, so 5, and then booyah. These are the two R values we need. If you want to be 99% certain there's a relationship, you need to have 0.959. If you want to be okay, 95%, 0.878. But what do you notice here, right? As I was mentioning earlier, as your sample size increases, let's say you get to, let's say you got to here, 12. If I had 12 shoe prints and the same correlation coefficient, I've met the criteria because my test score of 0.59 is bigger than the critical of 0.57. But we only have 5. Right? So if the question asked what sample size would make this significant, you would say 12. And again, please, wherever possible, make a graph. Make it makes your hypothesis test a little bit more legitimate. Right? The idea is there's a critical region, it's a two-tail critical region of R. And where do we fall? Well, we have 0.591, which is clearly not in the rejection zone. Right? Now, if you show me that, I'm like, wow, you really know what you're doing. Okay, I don't have to try and guess if you know what you're doing. And then you say, right, I guess you could say part 1 is, what do you know, right over here, part 1, up here. Part 2 is a hypothesis test. Statements. I guess step 3 here is just figuring out because your R value would have calculated here. Step 3 is here. Right? And then let's say step 4, and this one is, what does this mean? Well, because because the critical score is greater than your test score, we fail to reject the null hypothesis. We fail to reject the null hypothesis. And then I want some sort of statement at the end that is in non-technical terms. And again, what does this mean? It means there is not sufficient evidence to claim there is a relationship there is a significant relationship between shoe size and height. And then always restate the certainty to which you tested this. Right here, we used an alpha of 0.05. Now, they call this the CSI question in the textbook. If you're looking through the textbook, they got some good material on this. Like they go through it just like on the slideshow, but in more detail. And they call this the CSI example because it's true, right? Like, let's say you're a detective on some sort of murder trial and you find a large shoe print at the scene of the crime, and your main suspect is Shaquille O'Neal, and you find like size 25 shoe, and you're like, well, according to our graph prediction, if you have a size 25 shoe and you're 7'1", that's exactly what it should be. But then a good lawyer would say, how do you know it was not a clown? Because they also have big shoes, right? You could have a guy with huge shoes and he's just, he's a clown. And I don't know why they have such big shoes, but it's kind of funny, right? So you don't know. These guys got the same shoe size. And this is how you would prove that. You could get off with something like this. So the idea is that if you look at the statements that they make there in the slideshows as well, they talk about something called correlation does not imply causation. Even if there was, and you'll remember this from chapter 1, not imply causation, right? In other words, big shoes, even if you had a sample size of 12, right? Like let's say you had a sample size of 12 and you had that R value of 0.591, it becomes significant, right? Because, if you compare that to your critical score of n equals 12 and alpha 0.05, you get 0.576, right? 0.576. And in this case, you would say it is significant, right? We have a correlation between, at this point, if you increased your sample size to 12, you would have a significant relationship or a significant correlation, but it doesn't imply causation because it sounds ridiculous, right? If you think about it, right, you can say that shoes at this point are correlated with height, but there's no way you can say that shoes cause being tall. Right? If you go and buy, like it sounds ridiculous to say, but now it kind of makes sense when you look in this way, right? Like you can't just go buy a bigger pair of shoes and grow 5 inches. As much as my 13-year-old self wishes that was the case. Now, in the case that a relationship is not significant. So, okay, if the relationship is not significant, this is important. So, in the situation where our R value is 0.51 and our sample size is just 5. So like what we just saw, the best predictor of Y is the average. Now, if it is significant, so I'll talk about this in a second. If the relationship is significant, the best predictor of Y is X. Of course it's X, right? Because that's what we're looking for. Y is a function of X in that case. So you would just plug in. Now, let's say it is significant. So if it is significant, you just say, all right, so Y equals 1.73. That's the slope of the line. And your intercept 125. So you would just plug in. Let's say you want to know, so the shoe length, let's say you wanted to know the shoe print of how tall should somebody be if their shoe is, let's just go with 33. It's a little bit out of the graph, but that's fine. It's not too crazy. So what should be, it looks like it should continue on at least till there. Who knows what happens over here? But for now, let's say you want to know what is the predicted height of somebody with 33. Well, you would just plug in, right, f of 33 so your predicted height of somebody with 33-inch shoes would be 182.09 centimeters tall. However, the relationship is not significant, right? We decided earlier that the problem is that the relationship is not significant. And so if I said, what is the best predictor of somebody whose shoe print is 33, if you don't have a significant relationship, then you just say, well, what's the average height of a person? Right? If there's no significant relationship, the best predictor is the average. Like if it's like the same thing as if you had no information on something, right, at all. Like if somebody said, guess my age, what would you guess? You would guess the average age of people or state students, right? If I didn't have any sort of other predictor, like if I didn't have an X variable and somebody says, what is my age? I would say, I think, what's the average age of people in Canada? I don't know, 40. When finding the critical score, the easy way is if you have 0.05 or 0.01. Now, I might mess with you on your final exam and not give you this alpha value, right? I might say, what if on the final exam it says, test the significance of the relationship at alpha equals 0.02 or something like 0.01 or 0.1. What about that? Right? Because at 0.02, you could say, well, it's not going to be significant because it's still, if it doesn't meet 0.05, it's not going to meet 0.02. But what about 0.1? How would you figure out this? Well, the way you're going to figure out this is coming up with a test. You're going to have to do the classical approach where you're going to have to figure out a test statistic for a t-score. Now that formula you can find right here. I think it belongs in chapter 8, but they don't have it there. They have it, right where it should be actually, maybe in chapter 10 here. Right, essentially it's the same thing. You want to figure out a test score. And as you can see here, it just uses R values instead of, proportions or averages. But this is the formula here. R times then what do we have here? So n minus 2, so that would be 3. So here I get 1.269. 1.269. So in other words, now I need to figure out where does that thing lie, right? 1.269. Where does this thing compare to some sort of rejection zone? Let's use the p-value method. And then compare it to 0.1. Well, actually, it's going to be alpha over 2, so we'd compare it to 0.005, but that's okay. It's a two-tailed test. So what's our p-value compared to this thing? Whoops. So what would I do in Excel? I think with Excel, if I want to find areas, I just do a regular, I think there's a function like this. You just go T distribution. I think we can do right tail. And then 1.269, and then you're going to need degrees of freedom. Now, degrees of freedom is tricky with this is another little thing with correlation or bivariate data that you should know. When you have two variables, the degrees of freedom are n minus 2. That's why they have n minus 2 over here, if you're wondering what the heck was going on there. So just to throw another wrench into it here, you'd have to go that, and then 3 T distribution right tail. That should give us our p-value. .15. So yeah, the same result as before, right? It's too big. 0.15. The point is, you guys can see here the p-value, which is greater than our alpha over 2. So fail to reject, and then same conclusion. Here's another nice way to put your kind of non-technical conclusion. Shoe size does not predict reliably. Something like that, right? That's a nice non-technical way of saying it. Given the information we have. Math. Just explain your thought process. That's really what it comes down to. Entertaining as well. So you have to wait a while.